Hey guys, this video is for page 13 of your interactive notebook called The Discovery of the Electron. So we're going to fast forward a little bit, about 100 years from our last page, and we're going to talk about a man named J.J. Thomson. And J.J. Thomson did an experiment called the cathode ray tube experiment. Now, the cathode ray tube was not invented by J.J. Thomson. He just used that to do the experiment that this page is about. A cathode ray tube is a glass tube that has all of the air pumped out of it, and it has two metal electrodes in it. One of them is called the cathode, hence the name, and one of them is called the anode. And when you connect it to a power source, a ray of particles shoots from the cathode across the tube to the other electrode, which is the anode. And so we're going to go to the left side of your notebook, and we're going to look at a picture of a cathode ray tube right here. So again, two metal discs inside of this glass tube that's evacuated. There's no air in it. One of them is the cathode and the other is the anode. And when we hook this up to a power source, that ray of particles shoots from the cathode to the anode. Now, you'll notice that in this particular tube, there's a hole in the anode, and the reason for that is to allow these particles to pass through, so they keep shooting all the way across the tube. Now, even though I've done this ray in green, the truth is that you can't actually see this ray. What you can see is the edge of the tube where it glows when the ray hits it, and that's because the tube has been coated in a chemical that fluoresces whenever it's struck by this high energy ray. Now, you'll see some cathode ray tubes where they've put kind of a screen in the background right here that also fluoresces when it's hit by the ray. So that's how we can visualize that ray, but the ray itself we can't really see. Okay, so what does J.J. Thomson actually do with this? So J.J. Thomson gets kind of interested about this cathode ray and is kind of wondering what it's made out of, and wonders that it might be made of electrically charged particles. So he takes a couple of charged plates and he puts them on either side of the tube. And then he repeats this with a magnet, and he even changes up the metal that the electrodes are made out of. And when he does this, he finds that the cathode ray actually bends toward the positive charge. So we're going to look at the left side of your notebook again. And this is an illustration of what happens in his experiment. It's the exact same setup that we saw before, but this time we have a positive and a negatively charged plate here, and you'll see that the ray actually bends up toward that positive charge. So of course we know that opposite charges attract, so this cathode ray, if it's bending toward a positive charge, must be made out of course, negatively charged particles. So on the right side of your interactive notebook, J.J. Thomson concludes that the cathode ray is in fact made out of negatively charged particles, and that these particles are much, much, much smaller than atoms. Now, this piece of information came from another experiment, and we're not really going to talk about that experiment. It's just important to know that he discovered that they were much smaller than atoms. So what does this actually have to do with the atom, right? So why does that actually matter? The reason is that these particles that make up the cathode ray, they have to be coming from somewhere, right? All matter is made up of atoms. And wherever this cathode ray is coming from, and it turns out that it's coming from the cathode, these particles have to be being ejected from atoms. And so he concluded that these particles, these negatively charged particles that are so much smaller than an atom, like 1,000 times smaller than an atom, are coming from inside of atoms, and he called them electrons. So these negatively charged particles that make up the cathode ray were called electrons. So how does this change the model of the atom? Well, J.J. Thomson knows already that atoms are neutral. Okay, so most matter is not made of electrically charged particles. Most atoms have a neutral charge, but they contain negative electrons. So he reconciled this by concluding that the rest of the atom was a positively charged sphere, and the inside of this positively charged sphere were embedded these negative electrons, and he called it the plum pudding model, because if you've ever seen plum pudding before, it has plums embedded in like a pudding. And on the left, we'll take a look at this model. So this is J.J. Thomson's plum pudding model. So you see this positively charged sphere here, the positive pudding part, and embedded in it are all of these negatively charged particles, which we call electrons. But the atom itself is neutral because these charges cancel out. So in the cathode ray tube experiment, it was these individual electrons right here that were being shot out of the atom and across the tube, and that's what actually made the cathode ray. So that's how J.J. Thomson concluded that atoms, in fact, are divisible, contrary to the ideas of both Democritus and Dalton, because you can actually separate from them small negatively charged particles called electrons. And this is the very first discovery of a subatomic particle. And in the coming pages, we'll talk about the discovery of a couple more. But this is it for page 13 of your interactive notebook on the discovery of the electron.